We're going to start with the eclipse. So, because there is a clear relation between, well, I hope you know what is the relation between calculus 3 and the eclipse.
At the same time.
Okay, that is really good relation. Yeah, they overlap. You do know what a parametric curve is. Parametric curve? Yeah. Okay. So so then the thing is, so everything is so celestial bodies trace parametric curves in space. Okay. So to illustrate that without doing this, rather I have a little spreadsheet here. Yes. So we can see what's going on. So it is a spreadsheet. There will be, as you may have noticed in the syllabus, there is a line projects. So in many ways, this is what your project might look like at the end, or at least part of it. So actually will be a written project, but at least there will be some computational part, and that kind of computational part, what it might look like. So you can certainly see what's going on here: sun, moon, and the moon is blue, Earth is green, and the sun is yellow. Okay, so the idea is certainly just to demonstrate, illustrate rather, what is going on in the solar system, and so rotation of the Earth around the sun, and respectively of the moon around the Earth. Okay, so we certainly, as far as this course is concerned, that we just know the answers to those questions. Okay, and we'll look into that. This is slightly more advanced because it is based actually on the physics and the what is that in the corner over there? If you recognize, anybody recognizes this? What, this one? Is it big enough? What is this formula over here?
Is it the inverse square law?
Inverse square, yeah, law of gravitation. Yes, the law of gravitation, which gives you the gravitational force, which by the second law of Newton is pretty much the acceleration, the second derivative, and multiplied by the mass. Okay, so if we're looking at this part, it is about the sun. Well, the sun is not going anywhere, but still we are looking at it as if it might, and it is affected by what? It is simplified three-body problems. That's what it is. Restricted three-body problems. So U is the location of the sun, V of the Earth, and W of the moon. Okay, so the moon is pulled by both sun and the Earth. Okay, so that's pretty complicated, but otherwise it's so small that it does not affect either Earth nor the sun. So as you can see, this is, if you look at the formula, the acceleration of the sun depends on what? U minus v, the distance between the moon and the Earth and the sun. Inverse square, as you can see, turns into there's a third power there. You see why?
Because one of the powers cancels up top.
Right, right. So in other words, in the denominator it's a number, and in the numerator it is a vector. So we're going to talk about vectors a lot. So that's one of the things how you do it. I here do x and y separate, x and y separately, and then in the denominator I will put the actual numbers are here. The distance between the Earth and the sun is over there. So it is used as the numerator, and then the distance is used in the denominator, and it is cubed. Okay, so that's the vector form of the law of gravitation. Okay. So, well, let me just run quickly the actual simulation. Okay, just push 9. And so, well, And what just happened? What just happened?
The moon lined up in front of the sun.
Yeah, in other words, the eclipse.
Yeah.
So as you can see, the moon got between the sun and the earth, and that was the eclipse. Okay? So it's a very simplified version, and in comparison to the reality, can you kill what's missing from the model?
All the other planets.
All the other, yeah, yes, they pull. They also pull. Yes, that's true. What else?
I mean, we can't tell the relative, like, not heights, but like heights out of that plane. We can't tell.
You mean the third dimension, right?
Yeah.
Yeah, the third dimension is missing. Okay, but certainly it is a legitimate way to visualize it in this simplified way, but it is the third dimension is there. We know that it matters. So why does the third dimension matter?
Because that's what we live in.
No, for eclipse, for the eclipse.
That's where it'll be visible, depending on where the sun is.
Well, let me.
Maybe like your percentage of how much it covers the sun, like it lines up or not.
Yeah, but it is more specific, like this. So it is the alignment of the sun versus the Earth's orbit. So this is the sun, this is the Earth. Okay. Then it is possible that the moon's orbit. Sorry, that is. I think it's just over here. Okay, and this is the moon's orbit. So if this was the case, a purely two-dimensional situation, so the sun, Earth within that plane orbiting the sun, within the same plane the moon is orbiting the Earth. How does that affect the eclipse? Well, let me ask you, how many eclipses will we have?
A lot.
One a day. With each
One.
chart.
No, not one a day, but not as many.
One per month.
One per month, right. So the moon makes a full turn, and every time it will cross the line of view between the Earth and the sun. So you have once a month you have an eclipse. But the reality is that there is some kind of inclined plane for the moon, and it is like 5 degrees inclination, and that's why eclipse is so rare. Okay, because the moon might be above or below that plane until it hits the plane. There's no so it might be there's no eclipse. It might be here somewhere. And it just hot. I think it's just hot. So the moon might be here above the plane, and then it does not have you don't have an eclipse, even though it might be looking like this. And this is the moon right here. Okay. Okay, so the third dimension you have to add if you want to be realistic. The numbers are unrealistic. Look at the mass. I gave the Earth mass 1. I mean, we're doing mathematics, so we can do that. We're not doing physics. We're not trying to predict the eclipse. We're just trying to illustrate the mathematics. And the mathematics means that the whole system should work no matter what the masses are. And I gave the Earth mass 1, the Sun mass 500, and the Moon is smaller 1,000. Okay. So and then I could just keep pushing recompute, and as you can see, it is more or less reasonable. Okay. What is the picture on the right, if you can guess?
The perspective from the sun?
No, from
The
there.
side.
Oh, from yeah.
There, right. So as you can see, there is really no change in the point of view, and you still have as long as moon crosses the path, the side of view, you'll have an eclipse. So which picture is the right one? What? Yeah, you can say that. It was a trick question. So, certainly in third grade, it is explained to the child that the sun, not what you think, the Earth is not in the middle of the universe. No, the sun is. Okay, so, but by now, you know that it's all relative, right? So, both of these are equally good. It just depends on where you put your coordinate system. To actually make how do you make a case for this over that? Eclipse doesn't help, as you can see. In fact, there was this mechanism you may have heard from 2,000 years ago that predicted the eclipses, okay, mechanical thing, and they use this. They use the geocentric model, and there's some gears to help them figure that out. So even though they did not think about Copernicus and having the sun in the middle, they still were able to predict eclipses. So eclipses do not depend on our understanding, predicting them, at least roughly, does not depend on on the Copernican system. So what do we have to introduce into the picture to make the case for this or that?
A third dimension.
No, not necessarily. Other planets, right? Then they will still be rotating. You can see that they are rotating around the sun, but here it would be all messy, very hard to predict. They would be, and that's what messed up with people a lot when they were trying to figure out. They were trying to predict eclipses, by the way, and all other things they used for astronomy, and they were using this system, and this part was okay. But if you want to know what's happening with the rest of the planets, and they were just all over the place, and they couldn't figure out the good way to explain it. So one of the theories was, by the way, is that the alternative theories that the Earth is in the middle, and sun rotates around the Earth, but the rest of the planets are rotating around the sun. So it's a compromise. So we're still in the middle of the universe, but at least the rest of them, it's just one step away from the better one. Okay? So, all right, so, okay, one more thing before we'll take a break. What happens if I make the Earth bigger? Say I put 50 here. Let me start over. So if I make the Earth 50, a large one. Oh, what? It's not typing. No, okay, there is a somewhere. Refuses to edit. Yeah, sometimes it just does not allow to edit the whatever. Okay, so unfortunately I cannot edit this spreadsheet right now because I'm locked out of it. So the editing is not up. What happened? What happened? Oh, okay, it is just elsewhere. So what do you think is going to happen?
It'll go faster.
What?
Faster.
Oh, you asked. You don't. No, it's not. Doesn't have to go fast. The initial conditions are the same. So the initial velocity of the Earth with respect to the sun is the same. I only changed the size, the weight of the Earth.
It's going to pull the sun around.
Yeah, that's the main thing. It will pull the sun towards it, even though it's still a 1 to 10 factor, but still the pull will be clear. So here it is. Okay, just a minute. Okay. So it's still moving, but the sun is starting to be pulled.
It launched the moon.
The moon is gone. Why is it gone?
Gets too shallow.
I guess
gravities
so.
of the
I guess
two.
so because it's actually easier to imagine that what happened. Let me give it 100. Because it's easier to imagine that it is the opposite happening, which is what? It falls on the
Earth.
Earth. That's right. Yeah. So that's not fun.
gone.
Yeah, it start moving, and they're kind of dancing around each other. Right?
That would mess it
Oh,
up.
I think they're getting close to each other. The moon is gone already, I don't know where it went.
Oh, you're about to lose the sun in the air.
Yeah, no, it's still on the right, so we are still on the Earth, right, so we can still see, it's not so bad.
Yeah.
I wonder if they're gonna
We'd be on
collide.
fire at this point.
What?
We'd be on fire at this point.
Maybe. I have no idea where the moon is. Where's the moon?
They hit that, right?
Yeah,
And disappeared.
Yeah.
It's in the center of.
Ooh, look at that. This is where it is. The position of the moon is over there. There's some very large numbers over there. So it is gone. It did not fall on the Earth, surprisingly. Okay, so let's